Hi, in the last few classes we have been discussing the moment of inertia tensor and the moment of inertia. Let me quickly summarize what we have already seen in this regard. First we saw that the relation between the components of angular momentum vector and the components of the angular velocity vector can be written as a linear transformation. You can write this as a matrix equation. Here L is a column matrix with elements Lx, Ly, Lz. I is a square matrix. It's a 3 by 3 square matrix. And omega again is a column matrix with elements omega x, omega y, and omega z. We saw that the elements of this square matrix I can be written as I alpha beta is equal to mi delta alpha beta Ri square minus Ri alpha Ri beta. Here Ri vector is the position vector of the ith particle and Ri square is actually Ri vector dot Ri vector. Ri alpha stands for the alphath component of Ri vector. Also, we are following the Einstein summation convention where the repeated indices here I is a repeated index, so it is summed over. So there is a sum over I which is understood. Then we saw that these elements actually transform like the components of a second rank tensor. In other words, these elements are the components of a second rank tensor, and this second rank tensor we called the moment of inertia tensor. Then we wrote down the elements of the moment of inertia tensor for a continuous system. There we had ijk is equal to the volume integral of rho of r vector r squared delta jk minus xj xk. Here, rho of r vector multiplied by dv, this gives the mass corresponding to a small volume element dv. Okay. Delta jk is again the Kronecker delta. Xj and xk, these are actually components of the position vector itself. This is the notation that we are using. X1 stands for x, x2 stands for y, and x3 stands for z. And instead of a summation before, now we have an integration because we are now talking about a continuous system. Then we noted that the relation between angular momentum and angular velocity can be written as a tensor contraction. Earlier we wrote it as a linear transformation, a matrix equation, L is equal to I omega. Here we said that I, the square matrix denoted as I, has the components of a second rank tensor. Omega has the components of a vector, but a vector is a first rank tensor. L also has the components of a vector, which is a first rank tensor. So what we have here is that we have a second rank tensor here, a first rank tensor, and then we get a first rank tensor. All right. So these sorts of operations are called contractions, right? Because a second rank tensor here combined with the first rank tensor gives a first rank tensor. So this is similar to we said that this is the generalization of the dot product. So we said we can write L is equal to I dot omega. This dot stands for the generalization of the scalar product, where we could write A vector dot B vector as the contraction of two vectors. This gives us a number without any index. Okay. Here also you could also write this as Li is equal to Ij omega j, where sum over j is implied. So here we are combining an object with two indices with an object with one index to get an object with one index. This is an example for a tensor contraction. In the case of scalar product also, we are doing the same thing. A vector dot B vector can be written as AI BI with sum over I implied. Here, this is an object with one index, this is an object with other one index, and together combining this in this manner, we get an object with no indices, okay, a number or a scalar, right? We said such operations are called tensor contractions. So we can write L is equal to I dot omega. Okay, remember, here these brackets, all right, these round brackets I have used to denote tensors. All right. So there may be a small confusion with notation here. This is the notation I am following here. All right. See, if you have a second rank tensor, we could always write the components of the second rank tensor as a matrix. Okay, but not all matrices, not all second rank matrices transform like a tensor. All right. So when I use a round bracket like this means that this is written as a matrix, but this is actually a tensor. So this round brackets suggest that, in my notation, it suggests that we have a matrix with components that transform like those of a tensor. The same is here. Here we have a column matrix, but the components transform like the components of a first rank tensor or a vector. Okay, same is the case for omega. Now this is not a standard notation. This is just the notation that I am using in these classes, just to avoid confusion. We then went on to define the moment of inertia and its relation with the moment of inertia tensor. We started with the definition for kinetic energy. Again, sum over I is implied here. So this is the sum of the kinetic energy of all particles. Since Vi vector is equal to omega vector cross Ri vector, we can write this as half Mi Vi vector dot omega cross Ri. Since this is a scalar triple product, we can write this as omega vector divided by 2 dot Mi Ri vector cross Vi vector, where we have used the property that A vector dot B vector cross C vector can also be written as B vector dot C vector cross A vector, or you could also write this as C vector dot A vector dot B vector. Written like that, what we have here is actually the total angular momentum L vector. So we can write this as half omega vector dot L vector. But L vector itself was written as I dot omega. So going back to a previous notation, we can write omega vector as tensor omega, all right, and we have a dot here, and L itself can be written as I dot omega. In other words, we have now an expression for kinetic energy which is half omega dot I dot omega. Here we have a double contraction, right? So I has two indices. It's contracted with omega from the right. It's also contracted with omega from the left. So what we have here is a scalar. Now we can write omega vector as omega n hat, where n hat is the axis of rotation. Then the expression for kinetic energy becomes half omega n hat dot I dot omega n hat. Now since omega is a number, it's just the magnitude of the vector. We can combine it like this. We can write this as half omega square n hat dot I dot n hat. This scalar quantity here is called the moment of inertia about the axis of rotation. So n hat is the axis of rotation, and n hat dot I dot n hat is the moment of inertia about the axis of rotation. This is a scalar quantity. Using the definition for I, we finally saw that the moment of inertia here is mi ri square minus ri dot n hat square. Please note that there is no bracket here. This is a scalar quantity. All right. So if I have I with a bracket, this is a tensor quantity. This is a second rank tensor, and simply I stands for the scalar quantity, which is the moment of inertia. The moment of inertia about the axis of rotation. And how did we get this moment of inertia about the axis of rotation? We contracted the moment of inertia tensor from the left and from the right using the axis of rotation, using the unit vector along the axis of rotation. Finally, we saw that this definition for the moment of inertia about the axis of rotation is actually the same as the definition that we have learned in our undergraduate classes, which was sum over I mi rho I square. So rho I is the perpendicular distance to the ith particle from the axis of rotation. So these are the same. The inertia tensor as well as the moment of inertia depend upon the choice of origin of the coordinate system. But the parallel axis theorem says that the moment of inertia about some given axis is related in a simple manner to the moment about a parallel axis through the center of mass. In the following, we shall try to understand what this actually means. In this picture, the origin of the coordinate system is denoted as O. The center of mass lies here, and the position vector of the center of mass is denoted as capital R vector. The position vector of the ith particle is given as Ri vector, and Ri vector prime here is the position vector of the ith particle with respect to the center of mass. From this picture, the relation between these three vectors is quite clear. Ri vector is the vector sum of capital R vector and Ri vector prime. And that's exactly what we have here. Ri vector is equal to capital R vector plus Ri vector prime. Let's start by looking at the moment of inertia about the axis A here. So here we have two axes, axis A and axis B. These are both parallel to each other, and axis B is passing through the center of mass. So axis B is actually an axis which is passing through the center of mass and which is parallel to axis A. Let's start by writing the expression for IA, which is the moment of inertia about axis A. And we can take the unit vector, the direction of this axis, as n hat. Both these directions are the same, so we can denote them as n hat. Now we know that the expression for the moment of inertia is IA is equal to sum over I mi rho I square, where rho I is the perpendicular distance from the axis to the ith particle. Now, if this angle is theta, we see that rho I is equal to Ri sine theta. Rho I is equal to Ri sine theta. Now, we see that theta here is the angle between n hat, the direction n hat, and Ri vector. So, we can write this also as modulus of Ri vector cos n hat. Okay, because if you find the magnitude of this vector Ri vector cos n hat, that would be modulus of Ri vector modulus of n hat sine of the angle between them. Modulus of n hat is 1 because this is a unit vector, so this is simply Ri sine theta, and Ri sine theta is exactly rho I that we need. Okay, so we can write Ia is equal to sum over I mi Ri vector cos n hat whole square. Again, the whole square here means we are taking the dot product, the scalar product of this vector with itself. Now we just substitute for Ri vector. Ri vector is equal to Ri vector prime plus capital R vector. Okay. Now we can distribute this cross product. So this can be written as Ri vector prime cos n hat plus R vector cos n hat. Now we just square this thing. Okay. Here we have got a square. We have got a square of the sum of two vectors, a vector plus b vector whole square. This would be a square plus b square plus 2a vector dot b vector. Okay, so that's what we do here. Here we have got the square of the second term here, r cos n hat square, and I'm just distributing this mi to both terms in here. So it becomes sum over I mi r cos n hat square. We also have the square of this term, which is mi ri vector prime cos n hat square. Okay, and then we have 2a vector dot b vector, which is 2mi r cos n hat dot ri vector prime cross n hat. Okay, I hope that's clear. Now we can carry out the summation easily over the first term, because the second term, in this first term, this r cos n hat does not have an I index. Okay, so we are simply summing over sum over mi multiplied by some number. All right, and sum over mi is just the total mass of the rigid body. So here we can carry out the summation and write this as capital M r vector cos n hat square. Now for the moment I write the second term as it is, mi ri vector prime cos n hat square. Of course there's a sum over I over here, but we can use this Einstein summation convention from here onwards. All right, so from here onwards I shall be using Einstein summation convention. All right, now earlier I did not use the Einstein summation convention because then we would miss the summation over I here. In this term there is no repeated index. All right, so that's the reason why I wrote sum over I from the beginning itself. Okay, now we have carried out the sum over this term. In every other term I is a repeated index. Okay, so here we have got mi, and the I is repeated here in Ri vector prime. Okay, so this becomes Ia is equal to m r cos n hat square plus mi ri vector prime cos n hat square. Remember there's a sum over I here. Okay, plus 2mi r cos n hat dot ri vector prime cos n hat. Again there's a sum over I because it's understood because this index is summed over. Okay, this is where we are at. We have an expression for the moment of inertia about axis A. Let's take a look at the second term here. Now here we have ri vector prime cos n hat. Now clearly the modulus of Ri vector cross n hat is the perpendicular distance between axis B and the ith particle. Okay, because this is Ri vector prime, and just as we said before, modulus of Ri vector prime cross n hat is this perpendicular distance. So what we have here is of the form sum over I mi rho I prime square, where rho I prime denotes the perpendicular distance between axis B and the ith particle. Now what is this? This is simply the moment of inertia about axis B. This is the total moment of inertia about axis B by definition. So we write this as IB is equal to mi Ri vector prime cross n hat. All right. We can also look at the first term here. This is m multiplied by r vector cross n hat, capital R vector cross n hat whole square. Again, modulus of r vector cross n hat. What is this? If you look at this, this is capital R vector, okay, and modulus of r vector cross n hat, just as before, it's this perpendicular distance. It's the perpendicular distance between axis A and the center of mass. All right. Now, if you had a single particle of mass capital M sitting at this point, the moment of inertia of that particle would be m capital R vector cross n hat whole square. Okay, let's now look at the third term here. Right, here we have 2mi capital R vector cross n hat dot Ri vector prime cross n hat. Let's just rearrange this and write it as minus 2 R vector cross n hat cross mi Ri vector prime. Right, I've just interchanged the order of the cross product here. I've changed the order of the cross product here. That's why I have a minus sign here. And this mi, I've just written it inside here. So this is n hat cross mi Ri vector prime. Again, remember, there's a sum over I. This is the term we are looking at, and in here we have mi Ri vector prime, which is sum over I mi Ri vector prime. Let's now go back to the definition for the center of mass. The center of mass, the position vector of the center of mass is defined as capital R is equal to capital R vector is equal to sum over I mi divided by capital M multiplied by Ri vector. Here Ri vector is the position vector of the ith particle. So this is basically a weighted vector sum of the position vectors of all the particles. Now you look back here, this Ri vector prime, what was Ri vector prime? It was the position vector of the particles. Ri vector prime was the position vector of the ith particle if the center of mass is chosen as the origin. So if the center of mass itself is chosen as the origin of the coordinate system, then the definition for the center of mass would give m capital R vector equal to sum over I mi Ri vector prime. But if you choose this coordinate system, if you choose the coordinate system with the center of mass at the origin, all right, you are choosing a coordinate system with center of mass at the origin, all right, then in this coordinate system, the position vector of the center of mass is simply the 0 vector, because the center of mass is at the origin of this coordinate system. Right? So in this case, R vector is 0 vector. In other words, sum over I mi Ri vector prime, sum over I mi Ri vector prime is actually 0. It's a 0 vector. Alright? This just says that in this coordinate system, the center of mass is at the origin. This is the position vector of the center of mass in the center of mass coordinate system, which means that this term is 0. Okay. Here we have the dot product between a vector and the 0 vector, which gives us 0. So by the definition of center of mass, the summation over I mi Ri vector prime is 0. Okay. Let's put all this together and see what we have found. This was the expression for the moment of inertia about axis A. We just found that this term is 0, and we found earlier that this term is the moment of inertia about axis B. Now what about this term? This is R vector cos n hat square. In the picture, capital R vector is this vector, this is n hat. Now let's take the angle between them as theta. Remember, it's not the same theta as we wrote before. This is a different angle, but let's write it simply as theta. Okay, so here theta is the angle between capital R vector and n hat. So modulus of R cos n would be modulus of r vector, modulus of n hat sine theta, and this becomes mr square sine square theta. Okay, but what is this r sine theta? So if you look at this capital R sine theta is actually the perpendicular distance from axis A to the center of mass. Okay, it's a perpendicular distance. This is, wait a second. If you draw the perpendicular line from the axis to the center of mass, right, this would be, the length of this line would be r sine theta. All right. So what we have here, this r cos n hat, the modulus of r cos n hat here, it is the perpendicular distance of the center of mass from the axis passing through O, right, or from the axis A. All right. So here is the parallel axis theorem. IA is equal to IB plus mr square sine square theta. That is, the moment of inertia about any given axis, right, IA. This is equal to the moment of inertia about a parallel axis through the center of mass, that is IB here, plus the moment of inertia of the body as if concentrated at the center of mass with respect to the original axis. Okay, so that's the term mr square sine square theta. This is the moment of inertia of the entire rigid body as if the mass is concentrated at the center of mass, and this moment of inertia is calculated about the original axis A. All right, this is the parallel axis theorem. Thank you.